Welcome. This is the Plastics Assembly Course Design, and it will be taught by myself, Bill McMaster. Quick background, mechanical design engineer, has been involved with plastic design, working in many industries, including the automotive, furniture, power tools, electrical, and you name it. So with that, let's get started. Our first slide we're going to talk about is types of assemblies. We're going to look at basically three types of assemblies today. The first one will be snap fits. The next one will be fasteners. We will wrap up with welding. Now that we know what ones we're going to talk about, let's look at some advantages and disadvantages of each assembly technique, and this way you'll know why to pick one over the other. Okay, we're going to start with snap fits. Some advantages of snap fits, as you can see here, are low cost. You can disassemble parts after being assembled. It's easy to assemble and disassemble them. The designer has lots of design flexibility on where to put the snaps in the assembly, which is a nice feature. Some limitations, though, you should be aware of. You will have a possible rattle condition. And what that means is because of the tolerant stack-up of the parts, say the cover and the housing could rattle in some applications, and that could be an issue. Many applications it's not, but you should be aware of it. The other limitation is force retention. Now, again, this wouldn't be, it doesn't apply to all applications, but to your particular one, it might, or you should be aware that it could. And what this is, when you deflect a snap, it's under stress. When it comes all the way back to the undeflected position, it's not under any stress. And if that's the case, that's not going to be a problem with creep or force retention. But if the snap doesn't come all the way back to the original position, it will be under some force and some stress and some strain, and therefore creep will come into play, may relax, and you may lose the snap retention over a period of time. The second type of assembly technique we're going to talk about today is mechanical fasteners. Now, these are screws, bolts, and other types similar to that, inserts. And the advantages of fasteners are they're a conservative design. If you're going to be converting a metal part over to plastic, chances are the metal part is using the fasteners today. That makes it fairly easy. Disassembly is possible. If you want to unscrew and screw it back together, not a problem as long as you have a tool to do that. Some of the limitations are torque retention. When you screw this cover down on a housing, basically you're putting the plastic in compression. And now you're putting stress on the plastic for a long period of time, and that's what we call creep. And we just talked about it a second ago, but creep is important in plastics. Another limitation would be a possible stripping condition. It comes to no surprise that plastics are not as strong as metals, and if you're going to disassemble and assemble something often, you can strip it out. You need to be aware of that, and obviously adding additional parts compared to the snap fits we just talked about is going to add some cost. The last technique we're going to talk about is welding. And some advantages of welding would be strength. When you weld two parts together, you get a very high bond strength. You can design it where the strength of the joint is actually going to be stronger than the rest of the part, and it will break not in the weld, but in some other location on the part. Creep is not a problem with welding because, again, there's no stress on the part due to the weld. As far as limitations for the welding, basically another operation, you're increasing costs. No disassembly is possible. Most of the time that's a disadvantage, but some applications where you don't want somebody to disassemble it, so it would be an advantage. And the last limitation would be something called flash. We'll get in more detail, but basically it's an appearance issue, and basically you're getting some stray material overlapping, and it's just not a nice appearance for your overall part, but there's ways to get around that. Jumping into snap fits. There are several different types of snap fits, but the two that are shown here, the cantilever and the cylindrical, probably encompass 95+% of the market. So we're going to really concentrate on just one of them today, the cantilever, and that probably is the bigger of the two, but that's for filled and unfilled materials. And since we're talking in general engineered materials, we're going to be talking about the cantilever because a lot of them are filled with glass and mineral. But you should be aware of the cylindrical snap fit. Even though we're not going to be talking about it in detail today, it is a good example of a cylindrical would be the cap on a bottle, say an aspirin bottle or like a Tylenol bottle. The cap actually does all the deflection, and it deflects over the bottle or the housing.
Next we're showing is an oil filter valve, an actual part. It's out there today, and basically it's a part with 4 snap fits on it. 2 of them actually hold a spring, and the other is just for alignment purposes. And basically what this part does is through temperature, it regulates how much oil is going into your filter. Next slide is showing the snap fit design formula. And for those of you out there that know your mechanical engineering, you're going to say that this is just a standard cantilever formula, and you're correct. It actually is. But a snap fit basically is a cantilever. Previous formula works very well. For most cases, we've had some problems in the past, and we kind of zeroed in and realized what the problem was. The problem with the cantilever design formula is for short beams, it is inaccurate. As long as you have a long enough beam, it's not an issue. But what we did to prove out our theory is to look at several different configurations, and you can see we have 5 different configurations over on the left-hand side of the slide here. And you can see from the curves on the right that if you have an aspect ratio L over T, and that would be length over the thickness of the snap, and if you're over, say, we'll say 5, the cantilever formula works fairly well, other than case 4 and 5. 4 and 5, you get a lot of additional deflection. If you look closely at the curve here, the left-hand side, the y-axis, if you will, is showing deflection magnification factor. So what that's saying is the cantilever formula will be magnified by this number on the axis here. So for instance, if you pick curve 5 and you look at L over T ratio of 5, and you can see, come over to the left-hand side, and the deflection magnification factor is going to be a little more than 2, probably about 2.1 from just eyeing it. So therefore, the actual deflection is going to be twice as much as what the conventional cantilever formula would predict.
Basically, we've taken that cantilever beam design formula that's been out there for years, and we've added a Q factor. And again, it's a multiplication factor. You're getting a bonus deflection, if you will, for shorter beams. Now, the next formula has the Q factor as well, like you can see here. And this is probably the most important formula we're going to talk about in snap fits today. And this formula here is probably, if you're going to design a snap fit beam on a part, or snap fit on a part, this is the first formula you're going to need to go through. And this will determine whether your snap is going to break the first time or survive many times. So if you do this one right, you'll have a successful design. Another important formula would be what we call the mating force formula. And basically, it's the force of W. W is perpendicular to the part here, if you will. And a good illustration would be if you have a cover and you want to snap it onto a housing, you're going to have to use the palm of your hand to push, and you're going to be in the direction of W. And that's why we're calculating W versus P. P, basically, your hands can't get in there. Your fingers wouldn't be able to get in there to deflect it. Obviously, it's interfacing with the wall, and it is moving, and there is a force P. But the important one in general is W, because that's what the average person is going to have to push on. And if you want to determine whether the average person can push that cover on or whether you're going to need some sort of fixture to do it, this is where you determine that in this W formula. I'll just go through some of these variables in this case since they're not totally obvious. P would be, again, the force to deflect that snap, which we're showing right here in the sketch. You would calculate that first right here with some of the geometry, and I think most of these are obvious. BT are from the sketch. Epsilon O or 0 would be the allowable strain of the material, and then you have L, which we've talked about earlier, and the Q factor. So that's fairly easy to calculate. So now that you know P in this formula, you need to know the coefficient of friction, which you can get from your material manufacturer of the material, You also need to know alpha, which in this case here, you can see right on the sketch here on the slide, is what I call the lead-on angle. Okay, let's go through an example. This example here, first we're going to look at the maximum snap deflection that is allowable before the part is actually going to break, and then we'll look at what is the mating force calculated to be. So with that, let's look at the given. Now, in a real application that you're designing a part, the given basically is going to be given by you. You're going to pick a material, not based on snap geometry most of the time, but by other characteristics of the material, either high heat, high strength, chemical resistance, whatever. So in this case here, the application called out for a Petra 130, that's a PET material, glass-filled material. Now the designer or engineer is going to, from experience, get some geometry factors. T here, in this case here, we're putting in 100 thousandths. An L, we're putting in half an inch. And then the width of the material, B, is 1/4 of an inch. And now from the material, we know what the modulus is, and we also know the coefficient of friction is 0.2. And alpha, in this case here, again, from your experience, we put in 30. The designer or engineer isn't experienced. You just guess at this point, and you go through this iteration a few times, and you can nail it down. The last one here, this actually is epsilon. This is the allowable strain, which is 1.5, and that would be given from the material manufacturer, and sometimes you can get that from a data sheet. Okay, with that, let's jump over that one important formula that we talked about earlier, that strain formula. We're going to plug that in, and now we're going to solve for Y over here, Y max. And you can see before we do that, in order to calculate Q, we're going to need to know what that aspect ratio, the L over T. In this case here, it's 5.0. Now we can pull that over from the Q factor. I believe this was from configuration 4. Go back to that graph. We can pull that off to be Q equals 2.0. Now we have everything in the Y max formula, and we just plug in the numbers, and we come out with the answer to be here 50,000. So what that's saying is 50,000, theoretically the snap is going to break. Again, pure theory, if 51 is going to break, 50 it would survive. A good design would put a factor of safety in here, and maybe you would make your Y max in your design maybe 40,000 or even 30,000. Therefore, it would never break in an application.
And continuing with the example, now we're looking for the mating force formula and looking for W. In order to solve for W, that force you're going to push with the palm of your hand, you're going to have to solve for P first. Look at the right side of the equation there, and you can see everything is in the given column, and you already have calculated some of it. So basically, you plug in the numbers on the second line, and you come up with a P of 16.2 pounds. From that, now you go back to your W equation, which we showed earlier, and now from there, now that you know P, you have all the other variables, so you just plug them in on that last line, and you can see W comes out to be 14.2 pounds. Therefore, what it's saying is it will take 14.2 pounds to push on this cover onto a housing. You can look at some human factors books out there to verify that the average person can do that. And if that's acceptable, great. If it's not, make it lower. And in this case here, probably the easiest thing in the equation would be to change alpha. Make that a less steep angle, and it'll be easier to push on. With that, let's move on to fasteners.
First topic we're going to talk about is self-tapping screws. This is an advantage of plastics because they're a little bit softer than some metals. Makes them much more easier to just tap right into them when they're being assembled.
Here we're showing a drill housing, and this is Ultramid 8233. This is a glass-filled nylon material, and you can see here these circular cylinder-shaped holes, if you will, are where screws are actually screwed into. And there's no form thread there now. The screw actually will tap into plastic itself, which is a nice cost savings. Another type of screw, which is a self-tapping screw, is called a plastite screw. And this one is designed just for plastics. And you can see it's a triangular shape. and it basically it minimizes the creep that the plastic will see, and we do get some high values, and it's used a lot in our glass-filled materials. Another type of screw which is designed just for plastics is called a high-low, and you can see why. One thread is high, one is low, and this helps distribute out the stress on the plastic a little bit better. Very fine threads are not good, like a machine screw, are not good for plastics because you're putting too much stress on the plastic and you're going to strip it. So talking about stripping, how do you minimize stripping? This is showing here that a good design is going to have a length compared to its pitch diameter of 2.5 times. So if your screw is 1 millimeter, then your length of that screw is going to be 2.5 or more. You know, you could make it longer and you're not going to hurt yourself. Although from the benefit there from stripping, you're probably not going to, you can see it does level off. You're not going to help yourself too much, but it never hurts to go, you know, maybe a length of 3 or a little bit more. Another way, and this is only for unfilled materials, is looking at your boss diameter. Here you need a boss diameter that's at least 2.5 times your thread OD, or you can look at your pitch diameter. They're fairly close. This is showing our test fastener that we have here at BASF, and we've done a lot of testing with this. We get a lot of useful data. It helps us develop materials, and it helps us assist our customers which screw to use for a particular design and really what kind of values you're going to get with a particular screw and a particular ID and a particular length. So a very useful tool for us. And the next slide is showing actual parts that were used in some of our testing. This chart here, self-tapping screw hole guide, I know it's an eye chart and we're not going to go over everything here. This is a good reference guide, and it gives you some general starting points for what the ID should be. That's really in the chart. And then we have some bullets here which can be useful if you're having some sort of cracking issue, whatever. It'll help you to minimize your cracking and to come up with an optimized line. Next topic is going to be molded in inserts. Here we're showing many inserts that can be inserted into your plastic part, and they're both female and male threads, as you can see. This is showing a schematic of a cross-section, really, of a insert actually into the plastic. And you can notice the knurls on the bottom here, the black cross pattern, if you will. That's going to help pulling it out and twisting. And you can see this one big slot here on the bottom right next to there. That's going to help turn resistance or torque resistance, if you will. Here we're actually showing an actual part. This was a chainsaw clutch cover, and it's actually not a threaded insert, but just a sleeve insert. And this helps minimize creep on the plastic. This helps you get metal-to-metal contact and really screw down part very tightly and not really form any creep on the plastic. Okay, molded in inserts. Why would you use a metal insert? Well, the reason would be increased strength. Again, we talked about stripping. This here would minimize any thread stripping of the plastic. And if you're going to disassemble and assemble something frequently, or the end user is, we normally say if you're going to disassemble it less than 10 times, go ahead with the threaded in insert. If somebody's going to disassemble and assemble this thing often, 20, 30, 50 times, then you may want to consider using a molded in insert, because this way you won't strip it. Some considerations is you're going to increase your cycle time if you're going to mold it in. You could damage the mold. You're putting in one of these inserts in the mold, and basically if it gets dislodged, it can actually crack your mold, and you can do a lot of damage there. And obviously you're increasing your overall cost by molding in one of these inserts. With that, let's move to welding. First type here that we're showing here is spin welding, and it's just what it sounds like. Basically, you hold one part. In this case here, the bottom part would be held rigidly, and then the top part is basically put in a chuck, and basically you're turning it, and you're going to press that against the bottom part, which is held rigidly, and basically create friction, and you're going to weld the material just from the heat buildup, and then you pull away and basically you have a nice tight bond. Here we're showing a fuel filter that uses this process, and again, it's a very efficient process. Another process is called vibration welding, and this can be used for very large parts as well. And here we're showing a cover that's welded onto a housing, and you can see the direction of which way it would go. One actual part that we have been involved with is an air intake manifold, and this would be vibration welding, and it's all around the parameter that's welded. And you can also see there's 5 circular areas, dots if you will, in the middle of the part. Those also were vibration welded for additional strength. So looking at the joint design, you can see here 2 different parts with different cross sections. Basically, the middle area is where it is being welded. You have the cross-hatched areas with the lines going both ways. That's actually where you're welding. Basically, the area that's entrapped here, it looks like a backwards L, if you will. Basically, that's where the material can flow, and therefore it won't get up to the outer part of the part and create a flash. So the welding sequence, we'll go through that. Basically, you have a part, you put it in a nest, the black part, the other part comes down, and basically you weld it, and you're moving it into and out of the page, and basically this is where you form the weld. And there's pressures both ways, and the red area is really where it's being welded. Here we're just showing some of the areas here, and I can probably explain this better, and maybe on the last couple of slides you weren't seeing exactly what I was talking about. But basically, 1 is the weld bead for the top part, and then 3 would be where the material is actually melting, where the 2 materials are coming together and you're using friction. 4 is that flash I talked about. It'll start coming out, oozing out of there, but we have a flash volume is all in 6, and it can't make it out to the outer part of the part, so therefore you don't see it. It's actually in there. If you cross-section it, you'll see flash, but nobody can see it without, cutting the part open, so therefore it wouldn't be objectionable. Another type of welding would be called hot plate welding, and it's just the way it sounds. Basically, you take 2 plastic pieces, in this case here we're showing pipe, you put a hot plate between them, you pull the plate out, and now you just push the 2 parts together and hold them, and basically you have a welded joint using hot plate welding. Here we're showing ultrasonic welding, actually used to move the parts up and down very rapidly, and it's a fairly efficient process for smaller parts. So with ultrasonic welding, there's a couple of different joint designs you can look at, and the first one being an energy director, which uses amorphous materials and crystalline materials. You can use either. The preferable one is amorphous materials, but crystalline materials are possible, but not really as strong as the next joint. The next joint is for a shear joint, and that is designed just in mind for crystalline materials, and that's where you'll get your strongest joint for a crystalline material. So what do these joints look like? Here we're showing the energy director. That little triangle on the left-hand side of your page there, where we're showing W/4, the width of the thickness divided by 4, that there is the energy director. It's putting all the energy at one point, and therefore you get to weld quicker versus if you didn't have that energy director there. It just speeds up your weld process. Here's a clever design if you want to minimize flash, do a tongue and groove, and basically the flash again would start off in that bottom groove and couldn't work its way up out to the outer side of the part. Here we're showing a shear joint. Basically you can see the red part sits on the orange part. Basically you got point-to-point contact. Now the bottom part is in a fixture, cannot move, and the top part basically is being hammered, call it hammered, with some ultrasonic energy, and it's moving up and down at a very high frequency. That creates a lot of heat, and basically it starts melting at that point contact, and it basically will slide down and keep that material molten the entire time, and therefore the crystalline material will create a very good joint. The material melting will stay melted. It won't crystallize, if you will, until you stop the process. The next joint is showing a shear joint as well, but this is with that flash trap design. This one with tongue and groove, similar to what we saw for the energy director. That concludes our presentation here. We just want to thank you for participating in this seminar here, and we would like you to visit our website. We've got a lot of information on assembly and other techniques, a lot of design information, a lot of material information, which is at plasticsportal.com. Thanks again, and hope to see you at another one of our EPP courses.